Okay, and then continuing with section 7.4, we want to find the inverse of the function given to us. So whenever we are asked to find an inverse, our first step is to just swap x and y, and then we go ahead and solve for y. So in example A, I'm going to have x equals 5 to the y. Well, in order to get rid of our variable in the exponent, okay, variable in an exponent, we have to take the log. Now we're used to seeing our exponent on the left, so if you want to rewrite that equaling x on the right, so it's easier for you to see, hey, we have to make our L, go for it. There's nothing wrong with that. So I have an exponent, so that means I'm going to go to logs. Log base 5 of x equals y. Well, there's our inverse function. We solved for y. Again, we're used to seeing it on the left, so if you want to call it y equals log base 5 of x instead of log base 5 of x equals y, go for it. Same idea with example B, and don't forget that we have that invisible e for our base of that log. So we start by swapping x and y. X equals natural log or log base e of y. Well, we can't just divide both sides by log because that's not how it works. So instead what we will do is we'll log loop. So we'll have equals x on the other side and log loop it. I'm starting with a log, so I want to end with an exponent, which is how I need to do my e. I have e to the x equals y. Or again, we like to have our y on the left, so we have y equals e to the x. In example C, I switch x and y, so I have x equals 2 to the y minus 1 minus 3. Before we log loop, though, you have to get rid of anything on the same side of your exponent or your log, depending. For us, we've got our exponent, 2 to the y minus 1, but we need to get rid of that minus 3. I can get rid of it by adding it to both sides. So then we have x plus 3 equals 2 to some power, and that's the variable we want to solve for is in that exponent. So we log loop it, and again, we can move that x plus 3 to the other side. So we'll have log base 2 of x plus 3 in parentheses equals y minus 1. Our last step to get y by itself is to add 1 to both sides. So I have log base 2 of x plus 3 in parentheses, then plus 1 equals y, or for us, put the y first. Oops. In example D, we need to swap x and y. So x equals log base 3 of y minus 5 plus 1. We are going to move that plus 1 first because I can't log loop until my log is by itself. So then I'll have x minus 1 equals log base 3 of y minus 5. Before we log loop, if you want to move that x minus 1 to the other side, since they're equal, you don't have to change signs or anything, you're just switching them. And then we log loop. So we have a log, we want to end with an exponent. So I have 3 raised to the x minus 1 equals y minus 5. And again, don't quite have y by itself. We need to first, or lastly, move that 5 to the other side by addition. So 3 to the x minus 1, and then no longer in the exponent, plus 5, equals y, or y equals 3 to the x minus 1 plus 5. In problem number 8, we want to graph our log function. Now, when we do this, the first thing I do is consider our parent log function. So our parent log function for this problem would be just log base 2 of x, right? That plus 1, or excuse me, that minus 1 is a transformation, and that minus 2 is a transformation. Our parent function is just y equals log base 2 of x. Well, from here, we can log loop it. Again, move the y to the other side if you want. And it becomes 2 to the y equals x. Now it's a little bit easier to see that when we make our table of values, we can do it using our parent function that we just rewrote. We can plug in our exponent numbers that we always plug in, -1, 0, and 1, and see what we get for our output, in this case, our x. When we plug in -1 for y, we have 2 to the -1, well, that's 1/2 for the x. And then 2 to the 0th, we get 1, and 2 to the 1st, we are going to get 2. Then from there, think about how your function is actually different from your parent function. Well, you've got that minus 1 attached to your x. That is a horizontal translation to the right one. So take all of your x coordinates and add 1 to them. So we've got 1.5, 2, and 3. And then take all of your y coordinates and shift them down to a vertical translation down 2. So take your y coordinates and subtract 2. We've got -3, -2, and -1. So the points that we want to plot are 1.5, -3, 2, -2, and 3, -1. We are going to be able to space these out pretty well, so we will do so. And we remember that our log function is an inverse function of an exponential function. So our exponential functions had horizontal asymptotes. Ours, for a log function, is going to have a vertical asymptote. We'll talk about what that'll be in a second. But let's start first with plotting those points. So 1.5, -3, 2, -2, and 3, -1. Now, our graph is going to have a vertical asymptote that would be affected by a horizontal translation. So that x minus 1 causes our vertical asymptote to move to the right at x equals +1. That also affects our domain because we can't plug in anything to the left of that vertical asymptote. Our range, oopsies, is all real numbers though. Just like how our domain for exponential function was in all real numbers. And there is our logarithmic function.